100 watts. For over a century, that number stamped on the glass of an incandescent bulb has represented one thing: maximum brightness. When you compare it to a standard 40-watt bulb, the assumption is universal. The 100-watt bulb will blind you, while the 40-watt bulb will provide a dim, ambient glow. But if we step into an electrician's workshop, we can build a specific theoretical setup that shatters this assumption entirely. We are going to wire these two drastically different bulbs together. We start by connecting both the 40-watt and the 100-watt bulbs to a standard 240-volt alternating current supply. Crucially, we are wiring them in a series circuit. This means placing the components sequentially along a single continuous wire. In this configuration, the electricity has absolutely no alternate routes or parallel branches. Every single electron that leaves the power source must travel through both the 40-watt filament and the 100-watt filament in turn. So, what happens to the light output of each bulb when we finally close the circuit? This specific wiring setup creates a physical result that entirely inverts our basic assumptions about electrical power and wattage ratings. The moment the main 240-volt switch is thrown, power enters the system. Instantly, the 40-watt bulb flares up with an intense, blinding yellow-white light. But if we look at the 100-watt bulb, the reaction to the exact same power surge is entirely different. The larger bulb barely registers. It emits a weak, dull red glow or remains completely dark. Right in front of us, the bulb rated for less than half the power is completely dominating the circuit. To understand why a mathematically smaller rated bulb physically overpowers a larger one, we must abandon our intuition and mathematically deconstruct the circuit. First, we have to completely discard the concept of wattage as a direct measurement of brightness. A manufacturer's wattage rating is simply a mathematical specification. It only applies when the bulb is connected in a standard parallel household circuit, where each bulb gets the full voltage independently. To see what that rating tells us about the hardware, we use the physics formula: resistance equals voltage squared divided by power. The voltage variable is locked in. Both bulbs are designed for a standard 240-volt supply. Because voltage is fixed, a bulb's rated power and internal resistance are perfectly inversely proportional. When applied to the 40-watt bulb, dividing by a smaller power rating massively increases the result. The 40-watt bulb contains a highly resistive, densely coiled filament. Conversely, dividing that same 240 volts squared by the larger 100-watt number yields a significantly lower internal resistance. The 40-watt label on the glass isn't a promise of low light. It is a direct physical warning that this specific bulb acts as a massive bottleneck for electrical current. Now that we know the 40-watt bulb is highly resistive, we have to look at the architecture of the wire connecting our two bulbs. The defining characteristic of a series circuit is its single continuous path. There are 0 alternative branches, 0 bypasses, and no shortcuts for the electrons to take. This brings us to electrical current, measured in amperes, which represents the physical volume of electrons flowing through the wire. Because there is only one path, we hit an unbreakable rule of series wiring. The current is perfectly identical at every single point in the chain. The exact same volume of current that manages to squeeze through the high-resistance 40-watt bottleneck is exactly what must pass through the 100-watt bulb. This is the exact opposite of household parallel wiring, where devices independently draw different amounts of current based on their unique individual resistances. We now have a severe physical clash. Two drastically different resistive environments are trapped, forced to share the exact same trickle of current. To calculate exactly what happens when uniform current hits uneven resistance, we apply Ohm's law. Voltage equals current multiplied by resistance. We are calculating voltage drop, the pressure required to force current across a resistor. For the 40-watt bulb, constant current multiplied by massive resistance creates a huge 180-volt drop. Conversely, the 100-watt bulb's low resistance yields a tiny voltage drop of only 60 volts. Professional electricians use multimeters in the field to physically measure this extreme voltage discrepancy across the terminals. Finally, we can calculate the actual real-time power dissipation using one last formula: power equals current squared multiplied by resistance. Since the current variable is identical for both bulbs, the actual real-world power they output is dictated entirely by their resistance. Because the 40-watt bulb has a much higher resistance, it physically consumes the vast majority of the actual wattage available in this circuit. The 40-watt bulb glows brightest because its high resistance forces it to hoard the available voltage, leaving the 100-watt bulb with insufficient pressure to even ignite. This specific behavior of series circuits dictates the design and safety protocols of professional electrical systems. For decades, technicians have built specific tools called series test boards to troubleshoot faulty equipment. By deliberately wiring a high-resistance bulb in series with a device under test, electricians can safely throttle the current, preventing dangerous short circuits while they run diagnostics. We also see this principle harnessed in consumer applications, most commonly in strings of low-voltage holiday and festival decorations. By stacking dozens of identical low-voltage bulbs in series, the circuit evenly divides the main 240-volt supply across every single filament, allowing them to operate safely without exploding. Applying the physics of series voltage drops provides a reliable method for achieving electrical safety and precise current control. But every series circuit contains a fundamental architectural flaw, a single point of failure. If just one filament burns out and snaps, the physical path is completely broken, and the current drops to zero instantly across the entire system. This highlights the hidden danger of the mismatched 40 and 100-watt scenario we analyzed earlier. Forcing 180 volts across a 40-watt bulb that was designed to share voltage equally creates immense thermal stress, guaranteeing that it will burn out and drastically shorten its lifespan. While series circuits offer powerful ways to limit current, they demand strict adherence to matched wattages and calculated voltage ratings to prevent a single bulb from triggering a catastrophic, cascading system failure.